Hey, what's going on, everybody? This video is a video that I recorded with my good friend Matt. You might know him as M Alpha or Matt E in some online circles. He has been an incredible challenge developer for a lot of the CTFs that we've put on in the past, between NomCon, ActivityCon CTF, others that we've done, GrimCon, etc. Anyway, he is a binary exploitation ninja, wizard, and guru, and I spent some time with him, and I actually have in a previous video, and showcasing some Pico CTF binary exploitation challenges. We recorded this video like 7 months ago, and I'm kind of the worst person in the world and never got around to uploading it, so I'm sorry, Matt. But anyway, I hope that you listening in and watching this get some good value. In this video, we're showcasing the Cash Me Outside challenge from Pico CTF 2021. You can still find the challenge online at picoctf.org. If you log in, you can select, hey, Pico CTF 2021, or search for the Cash Me Outside challenge. It showcases Tcash and binary exploitation, which was new to me, so I learned a little bit, and I hope you get to learn a little bit just as well. Matt is a phenomenal teacher, and he does a great job with this stuff, so I hope you enjoy. I'll see you at the other end of it. I love you. Take care.
So this is the cash challenge from Pico CTF. It's a very basic Tcash exploitation challenge. I quote basic because whenever it comes to Heap, it's very intimidating. It can get very complex pretty easily, but this challenge is a very good introduction. So let's just first open it up in Ghidra. So I have Ghidra right here, and if you want to follow along, that would be in case you have any questions about why I'm doing what I am doing, because I've done this for a while, and I've done this challenge, so something that I might explain might not be understandable to other people.
Yeah, so I am not familiar with Tcash because I'm a binary exploitation noob, but I will more than definitely pick and poke and prod at you asking questions like, WTF is that? So
yeah. All right, so first we're going to open it in Ghidra, analyze it. Default options are fine. Let's go to the main function. All right, cool.
Oh boy.
So as you can see, there's a lot going on. A lot of this really isn't important, but the one thing that is important is right here you can see it'll open a flag.txt file. And after it opens that, it will read it into a variable, the local 58 variable. So right now, we're going to need a flag.txt file, and we're just going to fill it with garbage data. So let's just do CTF win. So there, now that we have the flag.txt file, the binary should run, which is fine. But anyway, it's going to open the flag, read it in, and you can see all of these hexadecimal characters right here. So what it's actually doing is, this is actually a string. It's just that Ghidra interprets it as a regular hexadecimal number. So that's why it's just showing up a little bit weird. Like if you were to take this and run it through, bin ASCII or whatever, you'll find that this is just some ASCII characters. Then after that,
is there a way, sorry, to have Ghidra like change the understanding of that to a string nice and easy? I've done that. I mean, I've seen that a lot, and when I try to copy out crap from Ghidra that's just represented in bytes or in hex, and then I've seen the comments like, John, if you just right-click on it and change the data to something else, it would do it. How is that?
Yeah, so what we can do is, you can see all of these undefined 8s.
Yep.
And you can see that the local 60 is where you have the null termination.
Mm-hmm.
So if we were to say, hey, this is 8, 16, 24... All right, this is 24 bytes, and this is the last,
byte.
think.
Yep.
Yeah, last byte. So this is technically a 25 byte string. So if we do Control L, we can change the data type. Sorry, that's small, but anyway, we're just going to type char, a open square bracket, 25 close square bracket. Then as you can see, it actually turns to a pointer. However, since Ghidra still doesn't know that it's an actual string, it's going to have this dot syntax.
Okay.
It can get a little bit ugly. So we could go, and actually spend the time to clean it up, but It's really just a string being copied to a variable.
Okay.
And then right here, it will loop through 7 times. So what it will do is it will malloc hex 80 bytes and store it in local 98, which is just a variable. Let's rename it as heap pointer.
How could you tell that was the heap pointer? Just because it's mallocating there?
Just because of malloc.
Okay.
Whenever you malloc memory, malloc is going to return a pointer to the allocated data on the heap.
Okay.
So after we do the malloc, whenever malloc fails, it returns null. So what this check is doing is it's checking to see, hey, if it's basically a null check to see if the check is null. If it's not, then keep going.
Gotcha.
Then right here, it's going to copy another string to that heap pointer. After we just go through what this program is doing, I'll show you what it actually looks like in GDB with the heap laid out to see, like, hey, these are just strings being copied. And then it will concatenate this variable, which is local 5.8, which, as you can see, is our... Where's local 5.8?
That was the read into the buffer for the flag.txt file.
Yes, yeah. Yep. So our local 5.8, let's...
Yeah, I don't know if you want to rename those. Yeah.
Flag buffer. Oh, I'm in data type change. Flag buffer.
What keystroke is that? Is that N?
So in order to change a variable or a label's name, it's just going to be L.
L. Okay, gotcha.
And if you want to change the actual type, it's Control L. Yeah. That's the one thing I really like about Ghidra is the key bindings are really nice. Because you don't have to go searching through menus or right click. So
it's just a matter of knowing the key bindings.
Yeah. So anyway, it's gonna concatenate the flag to the string that's already on the heap.
Gotcha.
Then after that, we're going to allocate some more memory, the same hex 80 bytes. We're going to copy over another string, and then we're going to set. And this is just the rest of the string, and then the null terminator to the string, and we're going to concatenate the local 78, which is the string we have above. So I'll just call this stack string. So nothing much really going on in this program. Just reads in a flag file, allocates the memory on the heap, and then copies some strings to the heap, and then copies the flag to the heap.
So my immediate thing, my knee-jerk reaction would be like, WT, what are those strings? Without us needing to go through and dehex or unhexify that, are those just nonsense? No, those look like regular ASCII.
It's regular ASCII. If we can go have a look at it.
We don't have to, but I didn't know if the point that you were going to get across is that, like, for our understanding right now, obviously that's not the flag. This is, okay, as one word that comes out.
Yeah. I mean, if they were actually doing some sort of operation on these strings,
right,
or if these strings are actually being used somewhere, then I'd actually go and say, hey, what are these strings doing? But since right now it's just literally this string is just being put on the stack right here. Mm-hmm. This string is just being put on the heap. This string is being put on the heap. There's really not much that we need to do to, like, figure out what the strings are doing. Gotcha. But what I could do is, for me, I'm not really, I don't want to spend the time, right-clicking, figuring out how to change these to actually strings. I would just run the program, set a breakpoint about here, and just look at memory.
Good call. Okay. And
so
I hope we can do that. Yeah.
Yeah, we'll do that after we get through this. So copies a string to the heap, copies the stack string to that string. Then it just is going to free one of the heap pointers. And it's going to free this other allocation right here.
Now that's another heap pointer, right? Just a different one?
Yes, this is just a different one.
Okay.
This one, the difference between these two is this one has our flag concatenated at the end. and this one does not. This one just has that regular stack string.
Gotcha.
Then we're going to printf. You may edit 1 byte in the program, and it's going to ask you an address. And if we figure out what type of data it takes %d, which is integer. So what we can do is we can right-click this and do retype global. We'll do char, and since it's %d, that's 2 characters plus a null byte. So it's going to be 3 characters. And now we can see that %d.
Nice. Okay, cool.
Then we have this right here, which is value, and local A9. You can see it's a %c. Well, it's a space because of that hex 20. %d. So that's 4 characters. Control L. And we have that space %c.
That was cool, and I think a neat thing for folks. Could you revisit that, or?
Yeah.
I don't know if there's a way to undo your edit there.
Yep.
Could you just walk through that mental? I know it was like a small trivial thing, but I don't know if folks often know that. Maybe I'm just stupid and don't. But you took that, what looks like a constant dat00 blah 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 memory address, and told it that specific string type.
Yeah. So whenever you have these variables highlighted in this like light blue, these are actually global variables. So variables that can either be stored on the BSS or on the .data section. But anyway, Ghidra has a tough time, will sometimes have a tough time of determining the types of these global variables. So that's why you see you have this underscore, this dat underscore, because it just wants to treat it as a void pointer. It doesn't know the actual type of it. So what we can do is if we actually double click in it, the listing view will hop to it, and we can see what the actual contents of this global is. And as you can see, this global only contains 3 bytes. And these 3 bytes are all characters. You have the %, the d, and you also have the ending null byte, because the strings in C are null terminated. So what we can do is we can tell Ghidra, like, hey, this is the actual type of the global variable. And once it does that, it'll say, okay, I understand this now. We'll actually print out the string. So if we
just Control L to change the type, right?
Yeah, Control L to change the type. And we're going to do char, because the char is a byte. And then it's 3 bytes.
Nice. The next one would be 4, because if you were to click into that, you see the extra space.
Yep, you see right here, this 20, this hex 20.
Yeah.
That's the space. Then you have the 25, 63, and then the null byte.
Cool.
So
sorry, I know that was like tiny whiny, but I don't know if folks... I don't know.
Yeah, it's typically whenever I am looking at a program and I see all of those like dat underscore, all of these global variables, I'll immediately just try to go through and figure out the types of them.
Cool.
Because then the decompiler will have a better time with that.
Much easier to read that now.
Yeah. All right, so this right here gets into some very pointer foo. It kind of looks a little bit confusing if you're not used to reading C or disassembly. But what it's doing is it's treating the A8 variable. So let's just call this pointer base. All right. And you can see this pointer base is null right now, but we feed it this base with the okay. Then after it does that, it adds this local A0. And if we look at this local A0, I know it's already it's a heap address just from looking at this. But if we just call this heap address, let's just actually call this input. Let's call this address input. Be more verbose.
Yeah, that's what I would have naturally thought to call it, just because of reading it's printing out, asking for an address, and then reading it from your input. How did you kind of piece that together that would be a pointer base for the heap address?
Yeah, whenever you're doing like indexing of an array, you typically start at 0 and then you add whatever index. So I was thinking, hey, this is going to be the start, and this is going to be the index.
Gotcha.
but it's just what it does, swap it around.
Okay.
So right now it will take this heap address plus whatever our input is and assign it to the value that we supply. So as you can see, we're able to edit 1 byte in the program, and it's able to be an offset of somewhere in the heap.
Gotcha.
So it's a very basic program, not doing much, just doing some allocations, doing some frees, and lets us edit a byte inside the heap. And you're probably thinking like, hey, how can you, read the flag if you can only edit 1 byte? But that's where Tcache comes into play. Crazy, crazy stuff.
I was trying to think in my head with my small brain, if we just clobbered one of the null bytes and then tried to print, I guess, from the top of it, would it leak sort of to get to the flag? Or I know that's not very Tcache-y.
Yeah, so as you can see, we have this puts, which is where we get our actual data out. And it's at local 80 plus hex 10. So if we try to find where local 80 is.
Just a line above it. I see that's
I'm in data type. So yeah, print base, right there.
Yep.
So as you can see, we have another malloc, and it's going to print from that allocation plus hex 10. So even if we did, overwrite some null byte,
yeah, it's a different chunk of memory.
Yeah, there's
right?
nothing past it.
Gotcha.
Exactly. And then as you can see, we can only edit 1 byte, so we can't just set that to something other than null.
So every malloc is its own chunk.
Yeah, we'll start to look at how these mallocs look inside memory.
Okay.
So first, what we're going to do is, in order to get this heap edit program running with this libc, we're going to use ponenit.
And all of these files that you have right now, aside from the flag.txt, you have the binary and you have this libc. You got those both from the Pico CTF page, right? Those are the provided challenge files?
Yep. All of this is provided.
Cool.
All right. I'm going to remove this heap edit patched and this sol.py stub. Then I'm just going to patch elf it myself. So what this actually did is it downloaded the loader for the program, and this is what will allow us to use this libc. But right now, this binary is not, set up to use it.
And I realized I stomped over that process. That was the ponenit command that you ran, right?
Yes.
And we showcased that in the previous video that we did, or at least I tried to speed run getting it set up for us. So if you want to go check that out, for anyone listening in, the first time we did the return to libc thing.
It's a very useful program.
Yes. Now what is this patch elf?
This patch elf will say, instead of using the system's LD, use this one in the current directory.
Now LD is the linker, right?
So I actually messed up in my last video. I called it the linker, but it's actually the loader.
Ah.
They both start with L and
but the D for the loader.
The DR. Yeah, it's.
I'm teasing.
I don't know. All right, so now that we have this configured to use this loader, in order to use this libc, we have to use LD preload. So we just do LD preload, which is an environment variable, and we use this libc, heap edit, the program runs, which is great. Nice. So let's just say address 0.
Can you zoom in on the LD preload though, just kind of mentally for a second? I know folks might know of LD preload. Maybe they are familiar with that sort of cheesy challenge where you could potentially overwrite a function in a program. What does LD preload do?
So LD preload it's a great system. What it allows you to do is run a program, but you get to specify what library you want to load in. So right now we want to run the program heap edit, but instead of heap edit automatically loading in our system's libc to use that library, we wanted to use this libc.
Gotcha.
Which is the one they provided.
If you were to try and run it without, it would just die. It would crash. Maybe.
Yeah.
Yeah. It depends, I guess, on the libc versioning thing. It's variable. Sometimes it does, sometimes it doesn't. Or Patch Elf already handled it for you, maybe.
Sometimes it does, sometimes it doesn't.
Maybe.
This
Cool.
generally it's not. Oh, I see now. So as you can see with running LDD on Heap Edit, which shows all of the dependencies for the program, you can see the program's already configured to use the libc in the local directory.
Okay.
So we didn't really have to run LD preload, but it's just good to know, like, it's just a good thing to know whenever you're wanting to use different libraries, different programs.
Perfect. Yeah, agreed.
Okay, so what we're going to do is let's just run this with GDB, and we're going to set a breakpoint in the program to look at these allocations.
Now you're using GDB with Jeff?
Yes,
Jeff.
Yeah, so GDB enhanced features. A lot of people like using Pwn debug for doing heap exploitation because it provides a lot of different functionalities for viewing data, viewing everything else. I'm just more used to Jeff, and I find it more, it's easier to learn instead of having to remember all of the viz commands, the tcache commands, the fastbin commands. It's just one command to examine the heap.
Sweet.
So we're just going to set a breakpoint, so B star, and then right now we have to do OX.
That address came from Ghidra?
Yep, came from Ghidra right before the call to puts, which is our you may edit 1 byte in the program.
Okay.
And we're just going to run it. All right, we hit our breakpoint. Zoom out a little bit. Now, to examine the heap in Jeff, you just have this heap command. So if we just run heap chunks to view all of the current allocated chunks, we can see we have some data. So all of these right here are all memory allocations with malloc. So we have this one at address 602.260. Its size is OX230. And here are the flags, which we really won't get into because it's out of scope of this video.
Did our program call malloc that many times?
That is the interesting thing. No, it did not.
Oh.
So right now you might notice this is a lot of allocations compared to what we found here. Whenever the program first calls malloc, what it will do is it will initialize the tcache. And this is where we're going to start to talk about what the actual tcache is.
What is the Tcache?
What is the Tcache? So to think about the Tcache, it's actually a very simple concept. What it is this big chunk of memory, okay, split up into 2 different arrays. One is just an array of integers, and one is an array of pointers. Let's see if I can actually heap glibc heap tcache. See if I can actually pull up something about it. Does this contain it? I don't think this has it.
Oh, Nightmare covers it. I saw an article in there. Cool.
Yeah, I don't know if he put in the actual structs about it. Yeah, this just walks through a demonstration.
Cool.
Which is, it's good. It's some of these, like demonstration code, like it can be a little bit hard to understand, but a lot of resources will just include some sort of proof of concept for some technique. So it's good to like kind of learn how these demonstration code works.
This almost looks pretty similar to our CTF challenge right now. So.
All right.
Why is it called a Tcache while you're looking around, if I could?
Yeah, so if you want to poke at my brain, Tcache stands for, I believe it's thread local caching, which means that every thread inside the program will have its own separate Tcache.
Thread being some running procedure.
Yeah, like if you've done any sort of like multi-threaded programming, either in Python, whatever language, you know that everything runs in parallel.
Mm-hmm.
So obviously, if you have one central T cache and you have two programs running in parallel trying to access that T cache at the same time, you can get a little bit of a race condition where one edits a value on the T cache while the other one tries to read a value on the T cache, but they don't know that they're doing that. So it's just, that's why each thread has its own separate T cache, because it wants to eliminate the whole race condition and everything.
Gotcha.
So let's zoom in right here.
Oh, nice. Okay, we found it.
Yeah, so all the T cache contains, which is right here. It's right when we first called malloc the first time. As it was doing that allocation, it was also allocating the memory for the T cache. So it contains this just char array counts with T cache max bins. And this is a constant, which I know is 64. You can just view it by going into the glibc source code. I know it sounds a little intimidating, but all that matters is you have a character array, which is a byte array of 64 values. And then you have a pointer array containing the same 64 values. So it's pretty basic to understand the actual layout of the T cache. You just have a whole lot of bytes and a whole lot of pointers.
Okay.
And then how this works is whenever you free a chunk, what will happen is the T cache will insert a pointer into one of these memories, which is the pointer of the free chunk. Okay? While it's doing that, it will also update the counts of that index. And each index refers to a different size. So let's say index 0 of the counts and entries arrays refers to only allocations of hex 20 bytes. So now whenever you free a chunk that's hex 20 bytes, it'll say, okay, we're going to go to the entries at the 0 index, put the pointer of that free chunk there, and we're also going to increment the counts to 1. Likewise, whenever you free another chunk, it's going to put that pointer there, then it's going to increment counts to 2. So is there anything a little bit weird, wonky there?
I'm still trying to wrap my mind around it. When we free a chunk, then it increments?
Yes. So the T cache keeps track of how many free chunks you have in memory.
Okay.
Not how many chunks are in use. How many are free?
So
and this is
freed as in they could be reused later, and that's why it keeps a cache of maybe that count, that collection of ones that could be reused. Is that right?
Exactly. So the whole idea behind caching allocations in general, not just the T cache, but also other caching mechanisms like fast bins or unsorted bins, is that doing an actual malloc is very slow and time consuming compared to other operations. So that's why when malloc occurs, they want to have it say, hey, instead of going through the actual algorithm of figuring out how much memory we have, figuring out, okay, is there going to be any overlap when we do this allocation? Okay, they need the size of this allocation. We just have basically an array of pointers that are valid saying, hey, here's our free chunk right here, use it. And it will use it.
Gotcha.
So that's the whole idea behind the T cache and just caching in general. So does that whole concept make sense of how the T cache itself just holds a pointer to the free chunk and the number of chunks that are of that size?
It's starting to. Yeah, I think once I maybe see it in action, sort of, it will make a little bit more sense.
Yeah, so what we can do is we can actually examine this struct in memory as we have the program running.
Yeah.
So let's copy this value right here. Let's use x /. Let's just do 32 8-byte values in hex. So if you're not used to GDB, X is for examine. 32 means we want to examine 32. G stands for 8-byte values in hexadecimal. So if we run that right there, so as you can see, there's a lot of null bytes and a lot of zeros.
Yeah.
But here at this index, we have a 0x2, which, if we look at the struct, is the start of our counts array.
And we had freed 2 allocations, right?
Exactly. Okay. And then right here, we have this 603890. And this is the start of our entries pointers.
Ah.
So now it's starting to kind of make sense.
Can I ask what that whole top half of all those null bytes are then? Is that just extra space?
So
in case you have a crap ton of freed allocations?
This is a fixed size,
which
is 64.
Okay.
So that's why there's all those null bytes.
Gotcha.
Also, another thing with the T cache is it will memset it all to 0, so that when it looks in the T cache for free chunks initially, it will see the 0. Because if you just put uninitialized data, that data could be like hex 99. So it says, hey, you have 99 free chunks at this address.
Okay.
Which can lead to troubles.
Sweet. Okay.
All right, let's go back to here. Now, the one thing we haven't covered is that these only store 1 pointer per size. Let's say you free 2 chunks that are hex to 0 bytes. Well, you only store 1 pointer. What happens to that other pointer to that free chunk?
Is that just gone?
And if it was gone, then the program would lose track of that memory area. And what would happen is that every time you'd malloc a bunch of memory, your program would just crash because you're out of memory.
Gotcha.
If you ever had memory leaks in like Chrome, where like you see, hey, my Chrome is using up 40 gigabytes of data, something of RAM, what's going on here? That's a memory leak, where it just loses track of how many allocations are and where they are.
Okay.
So what happens is this pointer, let's say in our example, we have hex 2 and we have this pointer right here. Well, at this pointer is a free chunk, but in the first 8 bytes of that free chunk contains the pointer to the next area that is hex 20 bytes that is also free. So if we were to see that in action, we have right here this area of memory, which is 06, and we have 2 free chunks, okay?
Now, I see that 603890 as almost the very last chunk that's displayed up in yellow there, those chunks from when you were looking at the heap chunks.
Yep.
Those correlate because it's the next entry?
So it's not really that it's the next entry.
Right.
It's just it's kind of hard to explain.
Sure.
Once I show you how this is laid out, it'll probably make more sense.
Okay, sorry. I'll stop asking annoying questions.
Yeah. So we have our entries of hex 20 in size, and we have 2 Tcache. We have two members that are, or 2 chunks that are hex 20 in size that are free.
Gotcha.
So we have this, and we have this pointer right here, which is our 603890, and that's our first one, okay? But then we have one more. So if we were to examine the byte, or the 8 bytes there, we can see we have another pointer. And this is the pointer to the next free chunk. So there's where our second free chunk of hex 20 bytes and sizes. It's like a linked list.
Yeah.
If you've done, data structures and algorithms or have studied that. So it's a linked list where each pointer is a pointer to the next free chunk. However, the size is kept through the index on this T cache right here, this T cache structure. And the actual number of elements in that linked list is also kept up here in the first area of this T cache per thread struct.
Gotcha.
So that kind of starting to make sense.
It is. I can see that they're tied together, sort of, into like that linked list idea.
Yep.
With this, okay.
And you can see how the pointers are stored in this T cache up here, and each index represents the size of each free chunk. And this right here represents the number of free chunks of that size.
Cool. I can press the I believe button.
All right. And then also, I should probably mention this. Definitely put this as a link somewhere, but the Pone College people, who are, the guy is the organizer for the DEF CON CTF.
Yeah.
He did a very good series of videos talking about the heap and went very much into detail about the T cache. So it's just YouTube, Pone College, playlists, and then where's the heap exploitation?
Oh, this is Artis. Yeah.
Yeah. But awesome. I'm trying to find where Module 9 heap. Tons of great video explaining T cache and heap reuse and everything else. Definitely worth watching if this is all confusing.
Sweet. Yeah, this is fantastic.
Anyway, back to this right here. So we understand how the T cache works. We understand we have two free chunks at this 603890 and this 603800. We also know that how the program works is we get an address, or an offset to be more specific, and then a value. And what we're doing is we're assigning this value to whatever that offset is. And this value is somewhere in the heap. So we can control a single byte somewhere in the heap. Okay?
Mm-hmm.
So how we can abuse this is after we write that value in the heap, we'll do another allocation of hex 80 bytes. Okay?
Yep.
Actually, sorry, this right here isn't for sizes of hex 20. This is actually for sizes of hex 90. Because as you can see, hex 90 is the size of this chunk right here. So it'd be 2, 3, 4, and so on. Just to clarify.
Sure.
Okay. The index will start here. So this would be index 0, 1, 2, 3, 4. And this index, which I think is like index 8 or something, this is 4 sizes of hex 90. So this pointer right here points to a free chunk, which is of size hex 90.
Okay.
Yeah, just to clarify, because this size will come into play.
Mm-hmm.
All right, so we can edit a value in the heap, and then we'll do another allocation of hex 80, which will round up to hex 90, because the heap likes to be aligned. So if you so let's just
our hex 80 does not equal hex 90.
So whenever you allocate a chunk, like this is the actual chunk of memory, but it will also keep a chunk header, which is stored right here.
Okay.
So what malloc will do is, in order to have this header right here, it will try to allocate so that it can have, this header at some area where the least significant bit or least significant byte is 8. So if we were to view 8, oops. you can see this is where our chunk header is.
Okay.
Now, what it will do is it will round up. So let's say you had a chunk that is, you know, OX28 or something. It will round it up to size OX30.
Gotcha.
And I believe with this one, I believe it will also round it up to OX90. I'm not too sure, or it might just stay OX80. We'll figure that out as we're going. So let's just step through this program. Let's do our printf, which is our address. Then we do the scanf, which is our offset that we want to enter. So let's just enter 0. So enter 0. Keep going. We have another printf, which is our value. And we're going to enter that value, put 0 again. And then here's where it actually does the movement. So as you can see, it moves one of our values to EAX. And it will add RDX to RAX. So if we were to print RAX, we can see that's our heap pointer. And if we were to print RDX, that's our index. Okay?
Yep.
So this is where the actual add comes into play. Then after it does that, it will store that value into RDX, and it will take AL, which is the value we supplied, which if we that's basically 0 in ASCII, this hex 30.
Right. Okay. Now I see.
And it will store it at whatever RDX is. So RDX should just be the same value that we had before, which is our 603480. And once we do that, it will allocate another chunk of hex 80. And you can see if we view the return value, which return values of function calls are stored in RAX. Well, yeah, the return value is this, which is the address because it's malloc.
Mm-hmm.
But if we were to use Jeff, the heap functionality, and do heap, but instead of chunks, we just do chunk.
Then that specify that address, that new chunk. Yep. Okay.
Yep. It will give us some information. So we can see its at address here that's actually of size hex 90.
Gotcha.
So it just decided to round up to the next 16 bytes. So chunk size of 144 and everything else. All right, cool. So let's start actually figuring out how we're going to abuse this. So what we can do is we can write a value at an offset in the heap. And then we do one more allocation. Well, what would happen if that offset in the heap was in the T-cache? To where whenever we do this next allocation, it will look at that pointer we saw. Let's do that back up. Examine. What if we edit this pointer to where instead of pointing to, you know, the actual free chunk, we point it to one of the chunks where the flag is contained.
Yeah.
That way, whenever we do that print statement or that put statement, it will be able to put whatever's in that chunk along with the flag.
Nice.
So that's how we're able to control how we can get this malloc to return memory to arbitrary locations. So let's try doing that.
Yeah. I think it seems like it's going to take a little bit of math. Is that right? To like
a little bit of algebra.
Yeah.
Not anything too complex. But all we just have to do is figure out we just have to figure out what this heap address is, subtract the address of that pointer in the T-cache, and that's our value we're going to edit. Or that's our offset we're going to use. So let's run this with GDB again. Let's just run it. Control C to break out of it. Deep chunks. Okay, cool. We can see. All right, let's find the address of this. So the address of this is 602080. Let's store it in notes.txt, or let's just store it in a solve.py script.
Now, do those address values change or like at runtime? Is there like an ASLR sort of thing? I know this is the heap and not the stack. Do those numbers change?
Yeah, so whenever you're talking about like memory protections of like ASLR,
Mm-hmm.
if we were to run checksec on this heap edit, we could see that there is no pi. And position ended execution, or pi, means that the binary itself isn't affected by ASLR.
Gotcha.
However, everything else inside the program, the stack, loaded libraries, depending on if they have pi, and also the heap, are affected by ASLR.
Okay.
But the one issue with ASLR is that whenever it's editing this address, it can only change these values. It has to keep the last the three least significant nibbles as the same, just based on alignment and relative offsets and everything else. So that's why if we want to edit a value, the only value we'll be able to edit is the least significant byte. We can't edit this value because we can't guarantee that this is a 3 every time. This might be a 9, this might be an F, this might be a 4.
Okay.
So if we were to try to do that, it would require some brute forcing, but we don't really need it. Anyway, let's take this, which is T cache direct. Cool. Then we're going to do our edit. I'm just setting up a very basic Tools script. And then once we do that, let's get the base of write index. There's probably a better name for that, but but we're just trying to find this value right here. The where it starts wherever we put a 0. So let's step through. We have to give it a value. Okay, so since we decided to Control C in that read, we're actually in this read inside of libc. So we have a lot of code before we can get back to our main function. What you can do is in GDB, if you type finish or FINI, which is the shorthand version of it, it will step out of the function call. So right now we're in IO new file, we do fini again, GI, and we can just step back to main.
Nice.
It is a very useful GDB shortcut. Okay, we have this printf, and we have our value in there. So we're just going to enter 0 again. Okay, and then here's where the actual add takes place. So we'll do P or X, which is the value that we supplied, P rex. And this is our base of the heap that we're going to be writing to. So let's copy this value. There, right there. So to figure out how far away we have to go, just basic subtraction. Subtract this base of the heap that we can write to by the address of the T cache.
Gotcha.
So let's do Python. Cool. 5152. So you just have to go back 5152 bytes.
Now that's in decimal.
Yep, that's a decimal. Luckily with us, if we look at the way the scanf is getting an input, %d
takes it in decimal.
Takes it in, well, it takes it in decimal, but it also doesn't require any like OX or anything.
Right.
So, and it also takes in negative values, which is very important.
That's what we need to do.
Because if this was only took in positive values, then what we'd have to do, which is kind of weird, but we'd have to do a wrapping add to where we supply it such a large value that it goes above 64 bytes and it actually overflows.
Cool.
But luckily for us, we don't have to do any of that math right there. All right, cool. So let's quit out of this. All right. P equals process. What I'm also going to do, just for help for me, I'm going to just put in if args.gdb, gdb.attach p. And
Nice.
this is very handy where if I were to run the program just as, let's just say, sol.py, it just runs the program regularly. If I were to run it with sol.py GDB, it will run it with GDB.
Nice.
So I don't have to keep editing the program for all of that. All right, so we have our offset, which is -5152. And it's asking for the offset, which is address. So let's do p.sendLine. Let's do -5152. All right, and then after that, it's asking for a value. So let's try to figure out what value we want to write there. So run it with GDB.
So I'm trying to think. If we were to tell it the right address as the new location, like through the offset that we just applied to get to, that brought us to the flag chunk. Is that right? Or am I forgetting?
It's so, and to, like the actual like heap flags, like if we go to heap chunks,
Yeah.
these flags aren't important.
No. I remember the capture, the CTF flag is what I was thinking.
Oh, yes. So if we were to examine this as a string, we can see we have our congrats, your flag is CTF win, which is the flag we specified.
Yep.
Because it's using stircat to copy the flag onto the heap.
Did we just supply that offset to get the address to that chunk that includes that flag? Or did we go to a different place?
What we did right now is we found the offset for the right, where if we do heap address plus whatever we input, we'll get to the T cache.
Gotcha.
Then we're going to have to figure out what value we actually need to write there.
Okay.
So after we do that, we're just going to step out of these functions with finish, go here, value. Let's just enter in a 0. So if we go back to our program, put in a 0. All right, cool. And if we do p_rdx, okay, you can see it's this big value. But after we do the add, we do p_rdx. We can see it's a small value because it does do some overflow internally. But since we were able to supply a negative value, the computer did it for us. So let's see. I think this is the right address. So let's examine g of x, and we can see we're not at the right address because we see a pointer right here. So let's try to figure out how far off we are. So our target is F088, but we're at F080. So we're off by 8. We need to...
Now you could tell that because it's like you're looking at that line where your cursor is, but the second column is going to be 8 bytes after.
Yeah, it's going to be 8 bytes over.
I see.
So like here's the starting at the least significant byte at 0, 8, 0, 8. Yeah.
Gotcha.
So what we have to do is we just have to subtract 8 from our value so that we don't go back as much. All right, so that's going to be 4, 6.
4, 4, 4.
4, 4. Yeah.
Quick maths.
Yeah, quick maths. As you can tell, I'm not a mathematician. I just do computers. All right, let's see. We're going to do finish to step out of it.
That was some good quick debugging in GDB, troubleshooting our thing.
Yeah, yep. Another thing with GDB, which I really like, is whenever you type in a command, like right now we have NI for next instruction. If I just press enter, it will run the previous command that I ran.
Nice.
So I don't have to type in NI for all of these. I can just press enter. Right now it's expecting input, so we put in our 0. And then if we do NI enter. All right, let's see what RDX is again after this add. So RDX looks like a same value. As you can see, ASLR affected.
Yep. But we got our
Value.
88, which is better than the 80 we were at before.
Mm-hmm.
And we have an
We
address.
have the pointer. We have an address. So right now we can edit any value in this address with our primitive of being able to just write what where.
Mm-hmm.
So let's try to figure out what value we need to write. So let's go shopping.
Ah.
So what we need to do, all we have to do is find an address in the heap where these values line up. So the 245A lines up because of ASLR. But we can edit this value so that this value plus hex 10 will print out our flag.
Okay.
So let's just try to find all values with the 245A. So 245A. All right. Cool.
Looks like we only have one realistic candidate that has a flag.
Yep. All right. So now we can't edit the 0, which is okay. But
set the 90?
Yeah, so keyword. Oh, I'm sorry. This is the address of the T cache. This is the address of the actual chunk. So it's 245B.
Ah, that makes sense.
And the 890. Yeah, I'm like, why is this value so low? It doesn't make sense. So yeah, so we have to just find a value where 245B exists, and we also have to find a value where 8 exists because we can only write 1 byte. So we can only edit this actual hex 90. We also could edit the 89, but we should be able to find some good candidate for where we just edit the hex 90.
Okay.
So 245B8. All right. So if we do 245B800, so just set this 90 to 0, and we were to examine this, we can see it's just null bytes,
right.
obviously.
The top of that are null bytes, yeah.
Yeah, but if we go back to Ghidra, we can see it'll actually print out from the base plus hex 10.
Ah.
So if we were to do this again, but plus hex 10, we can see we print out our flag, or lag is whatever.
Right.
So if we just take this hex 90 and set it to a null byte, what will happen is malloc will allocate at this address, even though it's overlapping, it doesn't do any checks.
Mm-hmm.
Then it will print out the flag. So let's try that. So quit out of that. Let's do a p.send line, and let's do a \x00. So we have to send an actual literal null byte.
Yeah.
Because it gets an input with %C. And if we just put in ASCII, 0, that would be hex 30. Yep. So let's see this in action in GDB. So let's finish out of this. Then use next instruction to go step through the program. Why aren't you getting it? Why aren't you taking that value?
Can you send a null byte in PwnTool?
You should be able to. Yeah, because it's getting input with %C space.
Right.
It should allow us to enter in a null byte.
Oh, do we need to have literally a space in front of that then?
I don't think so.
You're right.
What the space does, it just means that it will accept spaces as inputs.
Yeah.
So if we just input a space, like actual press space bar, then we get the hex 20. Let's just try. Let's try this. So what I'm going to try is I'm going to try to make it so that whenever it does these send lines, it will actually wait until we receive some sort of input or receive some sort of stuff back in the program. So we can just use a helper function called sendLineAfter, which will send line after we receive a string. Maybe address.
Oh, that's slick. I hadn't even seen the sunlight after one.
Yep.
I would always use like receive until and then make it super janky.
Yeah, so we'll just send line after we receive the string. It's great.
Okay.
All right, let's try this. All right, back to the main function. There we go. That worked.
Nice.
So it just seemed to wanted to add that null byte in with this right here. So we just have to wait until the value. Cool. So here we're gonna move the values. Here's the actual add. Let's print RDX. All right, this should point to our T cache, and this is the value we're gonna edit. We're gonna edit this 90. And here's where it does the actual write. So we'll take AL, which is 0, which is what we supplied. All right, it's RDX. So if we use step 1, and if we examine RDX, we can see it's actually null now.
Great.
So now when we run this malloc, malloc will return that address we put in the T cache. So we're to the next instruction. And we do P RAX. We can see it's this 9800. And if we were to examine heap chunk there, you can see it gives us information about it. We just do heap chunks again, 800. We have an allocation right here. And it will print out here plus hex 10. And right now, the program, if we continue, should print the flag. And it does.
Awesome. Okay.
So there, we can just run it against remote. Go back here, change this to remote. I'm missing a quotation. There we go.
Nice. Cool.
T-hash poisoning.
Okay. I think that started to make more sense to me as it developed.
Yeah, it's a lot, I know. Once you branch from ROP to heap, it's a big jump. As you can see, the whole, the challenge itself was just sending two values.
Right.
Actual figuring out, hey, this is what we need to actually edit in the T cache to get this to do what we want it to do. It takes a little bit of effort to figure out.
But since it is essentially connected, like you said, all tied together, like linked list sort of thing.
Yes.
When we were able to run the last malloc because we had modified the T cache, and malloc would reference that. Is that right?
Yeah, exactly. So this is another thing. If we were to examine the values here, it's
program's dead now.
But as you can see, it's all null bytes.
Right.
So what will happen is whenever we'll do another allocation of hex 90 in size, with this libc version, it doesn't do any checks. So it will literally try to allocate memory at hex 00000.
Gotcha.
That's where like a lot of people are very intimidated by the T cache, like, oh no, it's this complex thing. But it really, in terms of if you get some primitive as this basic, write 1 byte, you can really start to do some interesting stuff.
Cool.
But yeah, also to mention, the libc version we were using was libc 2.27. So I believe Tcache was introduced in 2.26, I want to say, either 2.26 or 2.27. But in 2.28, 2.29, and all the other recent ones, a lot of protections were put into place.
Oh.
So what we just did to where we edited that value, there would be a protection put in place saying, hey, this chunk in memory is actually in use. Don't allocate. And
Gotcha.
The program will just stop. So that's why they gave us this libc, because we needed that. We wanted those protections turned off.
Roger. Okay, so that is specific to this version of libc.
Yes.
Huh. Well, now we know.
Yep.
2.27, no longer to be trusted.
Yeah. It's funny because if you were to look up, like, I think it's Ubuntu 16.04 or 16.10.
Yeah.
Like, that was running 2.27. So you think, you have something as basic as editing a value in the Tcache, you could easily get code execution. It was pretty recently when they put the protections in.
Wow. Well, sweet.
Yep.
That was very cool. Thank you for showcasing all of that. That was a little bit more of a whirlwind than last time in my mind, but
yeah, these Pico challenges ramp up, I will say. It starts out pretty easy with stonks.
3,000 solves, then 270.
Yeah, and then it really gets up.
Cool. So is this what you would consider the entry point to looking at heap exploitation? Is Tcache like dipping your toes in the water for the rest of the dark arts?
So in terms of branching off into the more advanced Tcache exploitation and the more of like advanced heap exploitation, this Tcache is definitely a good start. And learning about the Tcache is a good start because once you understand the Tcache concepts, it's really easy to just make the heap allocate memory wherever you want it to.
It seemed like GDB and Jeff was like the vessel to make that easiest. Like that heap command and chunks and being able to take a look at it was, it seemed like it really streamlined things for me because it just shows it to you right there, and I would have no idea how to do that otherwise.
Exactly. So there's also Pwn debug. Pwn debug, what they do is they like to differentiate. So if you were to write Tcache, it will show you the information about the Tcache. If you were to write fastbins, it will show you the information about fastbins, which is another caching mechanism. Or if you were to write unsorted or whatever. So it gives you that more flexibility on what you want to view and what you want to do. The reason I just preferred Jeff for this one is because we don't want all of those technicalities. We just want the basic, hey, here's the heap.
Cool.
Now, in terms of other basic heap exploitations, use after free is a basic one. The thing with the use after free is it's its own sort of category within it. You can't really extend off of a use after free where you can extend off of a Tcache poisoning.
Sweet.
Yep.
Are there others kind of along that line in Pico CTF that might be kind of cool for us to maybe take a look at in the future next? Or
unsubscriptions are free as a use after free.
Yep.
These are all of the Pico ones. There we go. So filtered shellcoded was a pretty fun one. This is more of a shellcoding challenge to where like you had to actually write your own assembly, but it did some weird things with the assembly, which you had to compensate for. Kit engine was browser exploitation, and I can't remember what stock. I think this was a format string, but there's not really much heap unless you get to the more advanced, ones. But Kit engine, download horsepower, and turboplan were all web browser. I still need to solve these too.
Super cool.
I haven't had time to look at them.
No, but, I mean, as you said, this stuff kind of ramps up and gets pretty tough. So
yeah, I mean, Kit engine was a very good basic introduction to the whole web browser, how that stuff works, which is pretty interesting in my opinion.
Yeah. Well, awesome. Anything else? Any other lasting thoughts? Or, I mean, thank you again and again for being willing to do this, as always.
Yeah. I mean, that's about it.
Cool. So, if anyone has any questions about Tcash, go annoy Matt.
Yeah. Yeah.
I'm kidding. Sweet. Well, I'm excited to see the comments. I'm excited to see the positive feedback on this thing. But thank you again and again
Yep.
for being willing to do this.
Yep.